Good evening, everyone. I mean, two of you, three of you. Just wait for a while so the number of people can join. In this today's lecture, we are going to talk about this, which is moment of inertia, and that is the important, you can say, most important thing of this entire chapter. In the next chapter, we are going to discuss. We will be going to discuss this rolling motion and everything. Okay. So just wait for a while. Meanwhile, if you have any particular question query from the previous lecture, so you can ask. In the previous 3 lectures, we discussed torque, angular momentum, and center of mass, velocity of center of mass, acceleration of center of mass, and why the bodies, what is rigid body all about, and why rigid body is going to be rotate in general. Then equation of motion for angular, you can say, for rotation dynamics also we done. In this class, we are going to talk about generally or in detail moment of inertia, and that is again I am saying very important, not only for different shapes, but to find the moment of inertia from different axes for the same thing is going to be important thing also. Okay, and you can say in this from this particular class or from this particular topic, you are going to get the a little bit more complex numerical problem, because the axis they change, and the manner and the moment the axis is going to be changed, automatically this this moment of inertia is going to be changed, because this thing is dependent on the axis. Clear, everyone? Is this clear, everyone? Just a minute or two so we can start. Good evening, everyone. Meanwhile, you can open your cameras. Okay, so this is the beginning, like law of conservation of angular momentum. In the previous classes, we learned this thing. So Newton's second law of rotation motion is nothing but all about this torque tau equals to dl by dt. In the same way, like we have a force for a linear momentum. Okay, like for a force, for a translationary or for a linear motion, we have a force rate of change of momentum, basically del p by del t, or you can say dp by dt. That is the same sense. In angular, we have this. So if the net external torque on a particle or a system is 0, then dl by dt is 0. And then similarly, it is going to be if dl by dt is going to be 0, so we know that dt is never ever going to be 0. So automatically dl is going to be 0 or dl is going to be 0, saying that L is going to be constant. Constant means L, the angular momentum, net angular momentum, either it can be L1, L2, L3, and so. It is not going to change. It is going to remain same, constant. Angular momentum, wait for a while. Yeah, so where I have angular momentum, or you can say the net or total angular momentum is going to be constant. Angular momentum of a system, may be particle or a body, remains constant if resultant torque acting on it is 0. L is going to be I omega if torque is going to be 0, and then I omega is going to be constant, and I going to be inversely proportional to omega, where I, we're going to talk about in this in detail what it is I. Since the angular momentum I omega remains constant, so when I decreases, angular velocity omega increases, and vice versa. Okay, so that is the simplest thing, where I, or you can say moment of inertia, let's talk about for a particle, or you can say normal sense, moment of inertia. Inertia. So as on the previous page, that is written, over there, and we know from the previous classes also, that is torque tau equals to I omega. So take it, torque tau equals to I alpha is the main. Okay, torque tau equals to I alpha, and we done this derivation in the previous classes also, where I is moment of inertia, where I equals to mr square and you can say MOI, moment of inertia of a particle rotating around an axis. Okay, rotating around an axis. What does it mean? Just a minute. The meaning of saying and stating that is nothing but, suppose this is my axis, and for this particular axis I have this circle. Okay, in this circular path, okay, on this circular path, if I attach you can say mass, and that is going to be rotate, that is your radius, and it is going to be rotated in this way. I mean, this is going to be rotate around this axis. This is the axis with angular velocity omega. Okay, and that is the mass. So we know from this torque relation, what is torque in general? Torque in general is nothing but, as we know, torque tau equals to R cross F. Is this clear now, everyone? And we say, and we know, okay, for this particular thing, as if I can draw, this is going to be my force. If I apply force in this direction, and this is going to be the radius vector. Okay, the properly drawn radius vector. So we can directly see that the force and the, this one is force. So the angle between force and radius vector is going to be 90 degree perpendicular, they both of them. So simply what we can write after this, we can write R F sine 90 degree. Clear, everyone? And then this torque tau is going to be R F directly, where F is nothing but mass into acceleration. And we know from the previous classes, I did this thing, A is going to be R alpha, where alpha is going to be angular acceleration. Clear? As we know, V equals to omega R. So dV by dt is going to be R d omega by dt, because R is constant here. R is a constant, radius. So linear acceleration is nothing but R alpha. From there we get this relation. Okay. So the moment I put instead of A, R alpha here in this equation 2. In this equation 2 now. So simply what I get, torque tau equals to mr square alpha. And then I can change this mr square into the I. So basically in rotation, here everything is going to be, we prove this thing back again, where I equals to mr square. So the better meaning of this is, as we know, we have a relation force equals to mass into acceleration, right? Here the same, whenever any particular particle or a body is going to be rotate around an axis, on a fixed axis, so this I, which is moment of inertia, is behaving, is treating like a mass terminology. Clear? So whenever we are going to find the mass, or you can say this particular thing, moment of inertia for a body, for symmetric axis. So for symmetric axis, the same like we done for center of mass thing. For center of mass for continuous body thing, what we can do, x center of mass for continuous body is nothing but x dm, right? Or dm. Got it? In this way we can find x for x, y for y, z for z. And if I want to find for whole thing, for, you can say, position of center of mass, so then what I can do, this r, position of center of mass, and that is r dm, and this, and then dm can be, if we have a linear mass distribution, so we have this, so that is going to be linear mass density, total mass upon length. And for this, if I want to find this dm, so that is going to be rho dl. Got it now? In a same sense, we have, if I'm going to talk about this surface mass integral, so that is going to be mass upon area, total mass upon area. In the same sense, if I want to find dm for, you can say, two-dimensional body, so then that is going to be rho dA, small area for that two-dimensional body and mass. In a same sense, it can be for 3D also. So we have three types of mass distribution, or you can say three types of mass density: linear mass density, areal mass density or surface mass density, and then volumetric, or you can say mass per unit volume. General density, or you can say general densities can be normal mass density can be found in this way. Is this clear? Okay. So from this analogous thing, why should I tell you? In a same sense, for continuous body, or you can say for unsymmetric shapes, we are going to find the moment of inertia also. Clear? I mean that I teach you in for a one particle, but if in general we have n number of particles, 2, 3, 4, 6, and 7. So generally for one particle we have mr square. For n, because r is going to be constant, right? So m1 r1 square, m2 r2 square. Here r is going to be constant, so you can find r square m1 m2 m3 m so and so. Okay, for total, or you can say total torque, total moment of inertia is going to be, for r constant, m1 r square plus m2 r square r2, m2 r square plus m3 r square, and so and so. So what we can do, r square m1 plus m2 plus m3 plus so and so. So that is going to be simply what we already done till now, total I equals to 1 to n mi r square. That is for single circular path. But if we have different paths also, what does it mean? If I can fix this axis, okay, suppose I can fix this axis. There is one particle, there is another particle, there is third particle, there is fourth particle, there is fifth particle. Let's stick to this fifth particle all alone. And here we have from this, okay, let me define the center also. Okay, suppose this is the center of mass. So from this center of mass, suppose for first particle I have radius this, for second particle I have this one radius, for third particle I have this radius, for fourth particle I have this, and for fifth particle I have this. But the same thing, the one thing is, all the different particles, even they are rotating with the same omega. Okay, suppose in this way, this is your m1, this is your m2, this is your m3, this is your m4, this is your m5. Clear? Is this clear now till now what I am doing? If it is m1, m2, m3, m4, so that is r1, that is r2, that is r3, that is r4, that is r5. And I want to find the moment of inertia for any particular non-symmetric body which have these 5 or 4 particles. Let me draw that also. Suppose this is this unsymmetric body containing these 5 particles. If I know the number of particles and if it is can be discrete. So what I can do from here, I total again. Now I can put I here also. Summation I equals to 1 to 5 because I have only 5 particles. Mi because m1, m2, m3, m so and so, and that is ri square. Is this clear? Clear na? But obviously for any particular continuous body I cannot find this, I cannot do this integration. I cannot do this summation with this total sum. So for continuous body, this summation can be converted into integration, and then simply if I choose this small dm mass, okay, and I can pick this r only from the center of mass, I can pick this r. So what it is going to be, okay, for continuous body, for continuous bodies or you can say you can write unsymmetric also. Continuous means unsymmetric. Even we are going to find the symmetric one. Okay, unsymmetric. Either a continuous can be for symmetric or unsymmetric. This I, moment of inertia, is nothing but going to be simply r square dl. Is this clear? Is this clear now? Nothing is going to be changed. This summation is going to be converted into this simple thing, which is integration. Or you can write capital R also if you want to. So this is center of mass r square d. Is this clear? So that is the main thing for this class, because everything is going to be based on this. So if it is not understood clearly in your head, let me know. And this is I put in the recall because after this we have the moment of inertia for different kind of system. Okay, like moment of inertia for a rod of length L, moment of inertia for hollow shell, for solid shell, moment of inertia for plate. Obviously, I'm going to give the derivation for at least one, how to find the moment of inertia for these objects, but to give the derivation for all the things, it is not possible. So that, I mean, for this reason, deliberately I kept this slide vacant, or you can say I don't put anything, just to give you the detailed relation what it is, moment of inertia. So in rotational dynamics, or whenever any particular rigid body is going to be rotate, so moment of inertia is nothing but it is a mass analogous, or it is a mass analogy for a rotational motion. Okay, like in a linear transportation or linear motion or translation motion, we have a mass. In general sense, for rotational thing, we have a moment of inertia for a unsymmetric, symmetric, or for a any particular kind of body which is going to be rotated around a fixed axis. And that is why the axis is going to be very important. Why should I say this line? And you are going to see in this class even, if I change the axis, so what is going to be? Nothing. Everything is going to be changed if I change the axis. Why so and how so? Just focus here. If this is my axis I, and I can choose now this axis. It's my choice now. In which particular axis, I mean which particular axis I can want to choose. So that is I prime, and that is the first one, I. So now you can see for this particle, it is going to be R0. For this particle, R is going to be very less. For this particle, R is going to be this. For this particle, R is going to be this. For this particle, R is going to be this. For this particle, R is going to be this. So the moment I change my axis, everything, or basically the perpendicular distance, this R is going to be changed. And when R is going to be changed, and that is the significant thing in moment of inertia, because it is have a 2 power m r square. Mass is going to be the constant. In you can say more than 95% cases, we learned this thing in the previous chapters. Mass is not going to change with time in general cases. But the moment I can change axis, R is changed, and the R is changed, whole moment of inertia is changed. Is this clear, everyone? Clear na? So choosing a axis, picking a axis is important thing, and you are going to see in the coming slides, it is going to be changed how. The moment I just changed, you can say either the type of a body, and that is why I give you this, because on the type of a body, it is changed also. For example, for linear mass density, you can understood from here even also. For linear mass density, my dm is going to be rho dr, one thing only. Clear na? But for aerial mass density, dm is going to be this sigma into what it is, 4 pi r dr, 4 pi r dr, or you can say if it is a this particular thing. Okay, suppose this is the 2D dimensional length, breadth, height. So area is going to be L into either dB, or you can say either B into dl. 2 dimensions is going to be played. And the manner and the moment I put 2 dimensions, automatically integration is going to be changed. Got it now? What I'm saying? Similarly, if it is a 3-dimensional, so for 3-dimensional, for 3-dimensional thing, I can write this dr, but this is what it is, mass per unit area, and area I can put, wait, I can put this is 4 pi r square dr. And what it is, suppose I can, wait a minute. Suppose there is a ball, okay. If I make a cut in this particular ball, so this ball can be converted into a sheet, isn't it? Clear na? I mean, obviously ball is a sphere, and a sphere is a 3D thing. First of all, don't confuse, it is a 2D. So that is why the main thing is, it is not 2D, it is 3D body. 3D body means 3 dimension, sphere. So if I cut a ball, so that ball can be converted into a sheet. And the area of a sphere is 4 pi r square. And the very minute thickness of this ball, suppose this is the thickness, in this way you can understand. Okay, suppose this is the thickness, very minute thickness of this ball is dr. So the area of a sphere, which is 4 pi r square, and dr is the small thickness, and that is how I can find the rho. Rho is volume. Volume is simply, volume is how you can find volume for any particular thing. Volume is nothing but area into length, and if I find dv, okay, so I can do area into dl, and the same thing I can do, I mean the same thing I can done in the above side. Area of a ball is 4 pi r square, sphere, and then dr. Got it? Got it now? Because I can do this, where I was, yeah. Rho dr, I mean dm is going to be then rho into dv. Okay, I change here. Wait a minute. Rho dv. And then it is going to be rho is going to be this, and dv is going to be basically this. This is your dv, so you can put the value of dv, and automatically then rho is going to be, because after integration then limit is going to be 0 to capital R, from this to this, everything is going to be changed. Got it now? So that is all about only dm, and I want to find I. So obviously for this dm, I, okay, on the above what I can do for 3D, dm is going to be rho dv, where rho is going to be this dv is going to be, this dv is 4 pi r square dr, but I want to find I, right? So di is going to be integration r square dm, and that is going to be rho 4 pi r to the power 4 dr, just putting the value of d. Got it what I am doing? So for different kind of mass density, this integration is going to be different. Clear? Clear na? Instead of this, if I can choose a simple shell, shell means ring only. For ring I have a sphere only, and then for a sphere my dm is going to be rho dA, and then for a sphere, okay, so much information on single page, I don't want to do that. For a sphere you can correlate this, it is going to be rho dA, and how you can find rho dA I can tell you that also. Suppose it is a sphere, okay, for this sphere dA, small area, suppose this is your small area, and that is your dr, and the perimeter of this sphere is going to be 4 pi r. So beta dA is nothing but 4 pi r dr. Got it? Is this clear na? dA, simple. This is your breadth, small dr, and that is your length. So for 2D, it is for 3D. For 2D, this dm is going to be sigma into dA, where sigma into dA is going to be 4 pi r dr, and then di, because I want to find di. So for di is going to be again r square dm, and that is going to be sigma 4 pi integration r to the power 3, because r1 is here, r square is there, dr. Again integration is going to be behave on this third power. Noted? So that is how it can be changed. Clear everyone? Clear? So these are the simple thing which you need to know for the constant bodies. Okay, and moment of inertia is mr square, simply the analogous of mass in rotational dynamics. Okay. Okay, this one done. Okay, so this one is torque and moment of force. We done this thing in the previous class. So let's re-revise this. Torque is a cause of rotatory motion, and in rotational motion it plays the same role as a force plays in a translatory motion. That is, torque is a rotational analog of force. We done this thing on a previous page also. This is all evident from the following correspondence between the rotatory and translatory. As you can see, torque tau equals to I alpha, force F equals to mass into acceleration, work done equals to torque into d theta, and then work done equals to force into displacement. Power equals to torque tau dot angular velocity, force into linear velocity. Torque tau equals to dl by dt, angular momentum L, and that is dp by dt, linear momentum. Clear everyone? Okay. Now this is something new, but it is equilibrium of a rigid body. What does it mean? If any particular rigid body is placed, okay, and I found a point where it is going to be equilibrium of a rigid body, means the net torque is going to be 0. So it is not going to move, it is not going to rotate. For example, this pen, I put this particular pen as a rigid body. Obviously it is a rigid body, so this pen is not moving, neither from in this way, okay, neither from this side or neither from this side. Why so? Because it is at equilibrium. But if I try to put this a little bit this side, so it is going to fall in this way. Basically my fingers is going to be, or my hand is going to be behave as an axis, and on this axis it is going to rotate due to its weight. Obviously due to its weight, because we don't have another force here. So that particular, I mean, for each particular kind of bodies, that is the equilibrium. Okay, we have a point where that particular the net total torque is going to be 0. In a same sense, we have for linear motion also, translation motion also. For example, for that thing we have 3 equilibrium points. Okay, one is going to be uniform, another uniform, and then said that. Okay. So for linear analogy, I do control. Okay, I want to give you this. Just a minute. As you can see, suppose there is a ball, I mean bowl, not ball. For this bowl, if I can put this, okay, and I drop a marble here, so this, the equilibrium point is going to be there at this center, right? Clear na? In a same sense, if I reverse this thing, so it is going to be stable equilibrium point. Why stable equilibrium point? Because after traveling this particular path, okay, it is going to be stated here, you can say uniformly. So this particular point P is known as stable equilibrium. For linear case, I am telling you. Okay, in a same sense, if I draw this bowl in this way, or you can do this thing. Suppose this is your one another manner to represent this. This equilibrium point is known as unstable. Why it is known as unstable? Because the moment this ball is going to be fall anywhere, either is this side or either this side. So it is not going to reach this particular point, or it is not going to able, I mean this is not, this ball is not able to come back at this particular point P ever. So that is why it is known as unstable equilibrium, and that is stable equilibrium. And we have one more another, and that is very easy, that is very basic. If it is a linear path, so on linear path everywhere we have a normal equilibrium. Normal means perpendicular to the surface, wherever or whenever you want to choose. Clear? Either you can pick a point A, either you can pick a point B. It's your choice. At A, at B, or everywhere on a linear surface, we have a normal equilibrium. So this is stable, this is unstable, and that is normal equilibrium. In this equilibrium, stable, unstable, normal, what does it mean? F net is going to be 0. The total force working on these systems, on these ball of mass m, is going to be 0. In the same sense, if I have a rod, okay, so what it is for a rigid body means, let's read it out. A rigid body is in equilibrium if the sum of the forces and the sum of the moment on the body are 0. Moments, you can say either you can say moment of force or either you can say moments, basically the torque. Okay, so if the net torque on this particular is going to be balanced out, or moment of force is going to be balanced out, and it is not going to rotate, so that is going to be said in a equilibrium of rigid body, or it is known as the equilibrium of a rigid body. What it is? Consider a uniform weight of length 2L, negligible thickness, and weight W. The rod is suspended at one end, okay, by a rope that applies a tension T vertically upward. The magnitude of T and W are equal. Means this weight is going to balance this particular tension force if I attach this particular rod of length 2L. If it is not balanced, so there is a tilt. Okay, there is a tilt is going to be in this side. Or for example, one simple example you can correlate with your day-to-day life. Seesaw game. In seesaw game, if the two persons are sitting together of almost equal weight, so they are going to balance each other. Okay, but if they are not applying, I mean if they are not equal weight, so this seesaw is going to be do like this, up, down, simply, right? Obviously, if it is going to be down, so the other side is going to be up, and that is unequilibrium. So for equilibrium, this tension force and this weight is going to be equal, or you can say the torque here, you can understand in this way also. Torque here, which is T1, and torque here, which is T2, is going to be equal. And then what does it mean? Torque 1 is negative of torque 2. Basically, net torque, which is torque 1 plus torque 2, is going to be 0. Is this clear, everyone? What I'm writing, what I'm saying? Clear, na? Like for example, it is not clear. For example, for linear case, for equilibrium thing, is what it is, where all the forces at the point where all the net forces is going to be 0. In a same sense, equilibrium of a rigid body, the rigid body is going to be balanced the tension. If it is attached, or if it is, you can say, apply with a wire or any particular, you can say anything. So the tension and the weight is going to be balanced out, or the net torque is going to be 0. Is this clear, everyone? Is this clear, everyone? Okay. Pranav and Mukeshwaram, beta, what are you doing? If it is clear, so please write yes sir, clear, so I can go ahead, move ahead. Okay. Yeah. So this is the principle of moments, and then you can see if the anti-clockwise movement and clockwise movements are equal, the seesaw is balanced, and this is known as principle of moment, or you can say this is also known as equilibrium of rigid body. So this is principle of moments, means the net moment is going to be equal. Okay, when something is balanced about a pivot, this is the pivot, so the total clockwise movement is going to be total anti-clockwise movement. Movement is again the torque thing. Total, this is the clockwise movement and this is the anti-clockwise. As you can see, both of the girls here in this picture almost have the same weight. If any one of them is having a unequal or unbalanced weight. So that is not going to be balanced in this way. Clear na? Means this torque 1 tau and this torque tau 2 is going to be equal. And that is why it is balanced. Clear everyone? So that is your clockwise movement, this one. Because clock is rotating in this way and anti-clock it is going to be in this way. Clear? Okay. So that is all about this principle of movements. Now this center of gravity. Like we have the center of mass, the same science, and we have a center of gravity. So what it is, the center of gravity is a theoretical point in the body where the body's total weight, where for center of mass we can find the total mass is going to be hypothetically, theoretically is going to be centered, or you can say visualized. Here we talk about weight. Clear? Weight is different as compared to the mass because weight is a force, mass is an intrinsic property. You get it now, this thing? So the center of gravity is a theoretical point in the body where the body's total weight is throughout to be concentrated. It is important to know that center of gravity because it predicts the behavior of a moving body when acted on by gravity. It is also useful in designing static structures such as building or bridges. Okay, means if we are making any particular bridge or structure, so the center of gravity is very important to find, because at the center of gravity we cannot apply the much amount of force. So if in any case any particular tornado or something is going to be happen, so we we need to take care of that point, because if the center of gravity is, you can say, going to be collapsed, the entire building, the whole bridge is going to be collapsed. Clear? There is a one saying like the army person or navy person or any particular military or defense person, they are not doing this march or parade on a bridge. Why so? Because if they are, if they want to, that is not related with the center of gravity, that is related to the frequency, because bridge is in the air and each particular particle or any particular particle is vibrated in its own cell. So if they are doing the parade, so if the frequency of their leg and the frequency of this particular moving particle is going to be matched, so that is the phenomenon is known as resonance, and at the resonance the high amount of force is going to be generated, so the whole bridge is going to be collapsed. Okay, is this clear now? Okay, so in normal sense, determining the center of gravity, I'm saying, determining the center of gravity of a symmetrical bodies. For simple shaped object, the center of gravity can be determined by the following ways. When we balance an object with the help of a string or an edge, the point at which the object balance is the center of gravity. Means, as in a simple for pen example, the center of gravity is going to be at the center. Why so? Because if I try to balance this pen, or you can say from this end, so it is not going to be balanced. So where the weight is going to be balanced for any particular symmetric body or for symmetric body or in general, so there we choose a particular point, a hypothetical or theoretical point, that is known as center of gravity. Another simple physical procedure employed to determine the center of gravity is as follows. The next page. Okay, suspending this particular plate given in the figure by attaching a cord to a point A. If I attach a cord to a point A and then attaching to the cord at point C, and then this in this way. So if I attach a, you can say, wire or a cord at this particular point, at this particular point, at this particular point, and this, so we get a particular same simple point from each point, and that particular point is basically G. Here is at that particular point G, the weight of this particular symmetric body is going to be balanced, and that is known as, what it is known as, center of gravity. Is this clear, everyone? Is this clear, beta, everyone? Clear now? Means basically for this particle, as you can say, for this particle, for this point, even for this, and for this. Sorry. This, if I attach a, you can say, string or any wire, so it is going to be balanced from this point, the weight. Okay. G, center of gravity, COG, where the entire, or you can say where the total weight of the body, where the total weight of the body is assumed. Clear? In a same sense, for continuous, for unsymmetric bodies, determining the center of gravity for asymmetrical bodies, we make use of calculus to determine the center of gravity. When the mass is not distributed uniformly, we denote the integration of a continuous function with respect to the weight using symbol SdW. Then the center of gravity is determined as follows. Center of gravity into weight is going to be Sxw. Obviously, if any particular, you can say, unsymmetric body, something look like this. Okay, so I can pick any particular point. Suppose in this x-axis I want to find, and I pick this particular small part, dw, where this dw is the small weight of this whole body. So here x is the distance from a reference line. Suppose I pick this particular reference line also. Wait a minute. Suppose I pick this particular reference line also. Okay, so this x is basically the distance. This is your distance. dw is the increment of the weight. I choose this, and then it is going to be increase. Means if I choose this small point, I can make larger, and complete whole body. And then same sense, and W is the total weight of the body. So we know that W is going to be nothing but mg, mass into its, mass into gravitational acceleration. If the body is having, if the body have mass m, but the mass of an object is equal to rho dv, rho v, right? Rho is volume, you can say rho is density and v is volume. Combining both of the equation, W is going to be rho v into g, and dv is going to be rho g dv, where dv is nothing but dx dy dz, because you can put this numerical, you can say 3 time integration into dx dy dz form, basically. Okay, so if we have a functional form of the mass distribution, means any particular, either the surface mass density, either the linear mass density, either the volume mass density. So we can solve equation for the center of gravity, Cg into W, G triple S x into rho x by this. This triple S is the equation indicates a triple integration. Triple integration, I can find integration over dx, dy, dz. Okay, so this symbol is nothing but Cg, the center of gravity, weight, into G into this is rho x y z dx dy dz. Either you can do in this way, triple integration altogether, either you can do in this way also. I mean, it's our choice, whatever the point, center of gravity into weight into G into rho x y z, when we do this thing with the dx. So yz can be treated as a constant, rho x y z dy multiply rho x y z dz. Okay, so everything in our hand, whatever the method, whatever the manner we can, I mean, we want to choose. Is this clear now, everyone? What I'm saying? Clear, everyone? Okay. So this is just moment of inertia. I already explained this in a great detail. what is moment of inertia and everything. Clear? So, okay, let's talk about it. What is moment of inertia? For a single particle, the definition of moment of inertia is I equals to mr square, where m is the mass of a single particle, r is the rotational radius. SI unit of moment of inertia is kilogram meter square. Simple, because kilogram is the mass and r square is basically r is meter. Moment of inertia and mass of an object are different quantities. It depends on both the quantity of matter and distribution through r square term. Okay, different quantities. Why? Because obviously in which manner, or on that page I clearly describe you, I clearly tell you guys, like it is dependent on the axis also. So the moment of inertia is saying or taken as an analogous thing for a mass, but if I choose the axis, so r is going to be changed, and if r is going to be changed, so the moment of inertia is going to be changed. So that is why in this way it is different quantities. And for SI unit per, you can say from the manner of SI unit, you can say mass have a SI unit kilogram only, and we have I, which is mr square. So the SI unit is going to be kilogram into meter square. So in that sense, it is also different. Clear now, everyone? Like we have a linear velocity is equal to r into omega. Omega is angular velocity, but angular velocity is d theta by dt. So that doesn't have any particular unit. Why so? Because theta is a number. Clear na? And d omega, which is d theta by dt, is having a unit of time inverse, having a unit as a frequency, not as a meter per second. Got it? What I'm saying, just a little bit again and again, because you need to know this thing. Theta, which is d omega, which is angular velocity, d theta by dt. So that is theta. Theta is a number, or you can say it is an angle. And we define angle in this way, length upon arc. So both are in meters, so that is a pure number. So if it is doesn't have any unit, but time have a unit, so that is the unit is time inverse. Same as a unit as a frequency, because frequency is also hertz. Hertz. So in the same sense, if the two quantities are almost equal, or you can say analogous to something, we can find according to the units also, or with the help of units. That's why I'm telling you this all the thing. Like someone you can say can be confused in this sense also. Why not omega is meter per second? Obviously it can be represented as a you can say meter per second, but it is not directly meter per second. And how it can be represented as a meter per second? And even with the help of this relation r omega, so omega is v by r, right? Meter per second into 1 by meter. Again, the same thing we can find it out. So in any way, either the help of the general thing, either the help of the SI unit thing, these are analogous, not equal. That is the meaning of saying this. Moment of inertia and mass of an object are different quantities. Is this clear what I'm saying since last 2-3 minutes? Clear na? Means it is analogous. Don't treat almost equal, or don't treat as an equal thing. They are the different quantities. Got it? Like for example, omega and v sounds like a same thing, behave like a same thing, but they are not same. They are entirely different quantities. Omega is an angular velocity, and v is generally a linear velocity. Velocity have a dimensional formula, meter per second, and you can say length per time, or displacement per unit time. But omega doesn't have the same thing, meter per second. Omega is having a you can say dimension of time inverse, which is frequency, which is hertz. Got it? So they are analogous. The word analogous is all about it. It depends on the both the quantity of matter m, which is mass, and its distribution, how it is going to be distributed. So that is simple. We already done this thing for a, you can say I mean, if you want to find the derivation of this mr square, you can do that, but that is not required either, and I already given to you in the previous stage. So now moment of inertia for extended objects, or you can say for continuous thing. Continuous bodies. So for better continuous bodies, what it is, divide the extended objects into many small volume elements, each of mass del mi. So we can write, I already tell you this thing even. So we can write the expression for L in terms of del m. So okay, that is net del, and that is going to be I. It appear like L. I in terms of del m. So I, moment of inertia, limit del m tends to 0, and that is, I mean, this is the way to convert your summation into integration, r square dm. With a small volume segment assumption, dm you can, I already tell you, that is rho dv. Okay, so you can change this into this, and you can put this in this. So I integration of rho r square dv, where rho is a constant, or you can say mass volume mass density, or mass density for a volume thing. The integral can be evaluated with the known geometry. Otherwise, its variation with position must be known. Means what it is, either you know the rho or its geometry, or if you don't know, so you need to know this. What kind of rho this is? What kind of density is this? Linear mass density is this? Surface mass density is this, or this is volume mass density. Clear, everyone? Good. So this is the moment of inertia for different quantities. I'm going to explain about 2 or maybe 3 in this, and then we are going to this, and that is, I think it is not in your CBSE syllabus, but deliberately I put for better understanding. Okay, then done. Okay, so let's take a break, because I need a break to explain all this thing. Okay, and if you know the thing of how we can find this, so it is good. If you don't, so it's good too. But the main thing, you don't need to worry. Yeah, the derivation of these are not going to come. Okay, you don't need to worry. But I am going to derive at least 2 to 3 from the given things. Clear, everyone? Okay, beta. So just take a break and 5 to 10 minutes, and then we are going to meet. Hello, 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 hello. Am I audible? Am I visible? Hello, beta. Hello, hello, hello. Are you there? Okay. See, we can find this thing. I can prove this formula first because it is easy one, and then we can prove this one also because this one is easy one. These two things are little take time, but these two are very easy. So, moment of inertia for some common shapes. Okay. So, as we know, I mean, in the moment of inertia L, okay, this is length L and mass M is going to be, if I want to find the moment of inertia for any particular end. So this is known as moment of inertia, long thin rod through a rotation with rotation axis through end. Through end means any particular end. Clear? Means if I attach my rod of length L and this is my finger is my rotation and axis, and this pen is a length of L. I mean rod of length L. So that is simply, if it is a one dimension thing, so I can do this. This is total mass per length. Okay, this is linear mass density. For this particular rod of mass M, capital mass M, and total length L, and if it is given, so I can do this. Is this clear, everyone? Clear na? Then I can pick any particular choice of small dl length element. Is this clear? And if it is dl length element, so I can do this also from this axis of rotation. It is going to be x also till this dl length element. So from for this particular small length element, the small mass is going to be rho dl. Is this clear, everyone? Is this clear na? Okay. And I want to find the you can say moment of inertia for small this dl element. So this is going to be di x is dm. Is this clear, everyone? Clear, everyone? I'm asking to you this. This is clear na? Because I is, okay, di is going to be r square dm. In this way we can do that, and then integration whatever the specification is given here. So here the end limits, or you can say limit, is from 0 length to total length L, and this is x. So for this small, I can put di is nothing but x square rho dl, or you can say rho dx. If I can do with the x system, so I can do dx. Okay, this is the small length element dx. So that is simply rho dx. Here I can do all the same thing, rho dx. Rho dx. Clear? Now I want to find the total moment of inertia. So that is I 0 to, okay, this rho is going to be taken out, and then 0 to L x square dx. The integration of this thing is nothing but I, this is going to be the same thing, and 1 by 3 length to the power 3, because x square dx is give me the integration of 1 by 3 L to the power 3. Clear, everyone? I can put this is ml and I can get the same thing. So I m by L 1 by 3 L to the power 3, and that is 1 by 3 ml square from 1. Is this clear, everyone? This one thing. In a same sense, if I want to find for this, now here everything is remain same. Di is going to be this integration, and then rho x square dx. But the main thing is changes here limit, because I can choose now the axis, and you can see directly in between point. So if it is the rod of length L, so this is L by 2 and this is L by 2, isn't it? Because I choose this rod of length L and it is going to rotate in this way with omega. So the moment I you can say change my axis, everything is going to be changed, and you can see in a while. Again, the same thing I can do. This is the small dx. Okay, this one is small dx element, and this is the x from the axis of rotation, and the same thing is going to be happen here also. Clear? Because it is the you can say linear road, so this rho is going to be m by l again, total length. But that you can say to find this total integration of, you can say, moment of inertia when it is going to be passes at the center through the, I mean when the axis is going to be passes through the center of a road, or you can say when a long thin road is rotating about the center, rotating axis through the center, so then it is going to be the integration limit is going to be something look like this, L by 2 to capital L by 2, and this is constant, we can take it out, x square dx. So better then it is going to be, this is taken out, and that is 1 by 3 is common, x to the power 3 limit L by 2 and minus L by 2. And when you solve this thing, so automatically you can get I, which is 1 by 12 m L square. Why so? As you can see, this is going to be L to the power 3 divided by 8, and minus plus, because cube of negative thing gives you negative, and negative is going to be become positive. So this entire thing going to be lambda by 3 into 2 L to the power 3 divided by how much it is? It is going to be 8 then. 8 3s are 24 and then 12. Yes, exactly. Clear? And you can put the value of lambda over there, that is m by L into 1 by 3 into 2 L to the power 3 divided by 8. Clear everyone? So in this way L going to cancel, and then 2 is going to be cancelled with this, so 1 by 12 ml square we can find it. Is this clear? So now we have a proof also. Okay, just a minute, I can do this a little bit. This is visible now? Yeah. So now we have a proof also. The moment I change the axis, in front of you can see the moment I can change the axis, entire moment of inertia is going to be changed automatically. Okay, and I can do this thing here to make a little bit good as a picturization. Just a minute. So we can do this. I lambda by 3, and that is going to be simply L to L by, okay, this is going to be my, instead of small you can put a capital thing if we put everything in a proper manner. Okay, negative L by 2. So that is very easy then. L to the power 8. Color thing is most difficult thing for me. L to the power 3 by 8 minus of L to the power 3 by 8, and that is gives me lambda over L to the power 3 over 8, and then it gives me 1 upon 12. I can write now directly because you know this thing, m L square. Clear everyone? Clear na? So as you can see, just for, I mean just sorry, the moment, the manner I can change the axis for a same symmetric body, for the same entirely same same thing, everything. The moment I can change my axis, the moment of inertia is going to be changed. Clear everyone? Now we can find for this scenario also. For this, okay, one thing is there, it is not thin spherical cell, it is solid spherical cell, and I'm not going to give you this because this is a long healthy derivation, that is solid sphere. For solid sphere we have moment of inertia I equals to 2 by 5. If you wanted to see how we can find it, this, so I can teach you in chapter assessment, you can let me know. Okay, 255 m r square, but we are going to discuss for this also. Is this clear everyone? We are going to discuss for this. So just a minute and you can get to know how we can do that. And then we have another shapes also. So I'm not going to describe, you can say derive everything. So suppose, or I can go to the next page. Okay, here and on the upward side we can, let's do on the previous page. Wait, let's stick to this page because everything is going to be there as a proof. Okay, so suppose I want to find this. Just a minute. I mean moment of inertia of a thin spherical set, and that is very easy. You're going to get in a minute. So this is my this shape, right? So this is the thing. Now you can correlate or you can say hollow sphere because it is a shell. So you can rewrite this thing, moment of inertia for a moment of inertia for a hollow sphere also you can write. Okay, so beta hollow sphere is nothing but 2D kind of thing, not 2D. Hollow sphere is this, or a ring. Okay, so this ring again have okay, so this ring have 3 axes. Clear na? It is a symmetric thing and it have 3 axes. Or what we can do, suppose there is a point of radius r. There is a point, this point. This is a small dm of radius r. At a point, this is the center from 0, 0, 0 to a particular point x, y, z. Because it is in 3 dimension. Sphere is a 3D. Okay, whole sphere it is. So how I can find, instead of directly, what we can do, what we can discuss, or we can do this thing. Instead of finding this directly, I can do dix, clear, and I can do diy, and I can do diz, and that is going to be dm integration y square plus z square. Now what is this thing? Okay, just focus a little bit. Suppose I can pick a x-axis. Okay, so the distance from the x-axis, okay, in this way you can understand. As you can see, on this particular x-axis, if I want to find the radius, so on this x-axis, if it is y-axis, so this is dy, and wait, on the from diagram you can understand, because if I'm going to give you this diagram thing, just a minute. Yeah, wait a minute. X, Y, Z, clear. So we have this, right? We have this, and we have this thing also. This is my X, Y, Z system. Is this clear, everyone? So this is my X, sorry. This is my Y, this is my Z, and this is my X. And how can I write X square, because dix is small dm into X square. How can I write X square equals to Y square plus Z square? So for any particular axis system in 3 dimension, the distance on X is going to be this thing. How so? As you can see, there is a Y, distance, right? Is this clear? Clear na this one? Good. And this is the X, this is the Z. So if I want to find X from this point, from this particular small point O, from this particular small point O. So how can I find X? How can I write X in general if it is going to be rotated in this manner? Or you can say if it is going to be rotated along this plane, in this way. So beta, here you can directly see that before drawing this, Now you can see that this x is nothing but it is a perpendicular. It is a perpendicular, right? In this, so this behave as a z, this behave as a y, and this is x. So x here I can write this is my x, and this x basically y square plus z square. So in 3D system, if I want to find the x for another two axes, so that is y square by z square. In a same sense, or you can write in this, you can understand in this way. Suppose this is my x, right? So y is going to be in this way. Is this clear? Y is going to be in this way, okay? And then z is going to be in this way. So this is base and this is perpendicular. So if I want to find the x-axis from this perpendicular, so this is x in this way. If this is the point of rotation, so this is x and this is y and this is z. So in this way, the x is going to be y square plus z square from this axis of rotation, from this axis. This is the axis of rotation. Containing y and z axis. Clear everyone? So in a same way I can write, okay, that is sufficient. In a same way I can write beta diy dm. For y thing we have x square z square, because it is, okay, diy is basically dm, y square dm. In this way you can understand dix is nothing but integration x square dm, and in the same sense diz is nothing but z square dm. So dm is going to be the same, small particle, we have n number of particles, huge amount of particles, that is going to be simply dm, and then it is going to be y square plus z square. No, z is not going to be x square. Clear? Now you can see dix, diy, diz is going to be constant because it is rotating in this hollow sphere only. So either you can find dix, either you can find diy, either you can find diz. And if you want to find the net total moment of inertia rotating this hollow sphere, thin shell around this axis, so how can I write? First of all, this dix, diy, and then diz is going to be equal. So the net moment of inertia is going to be total small moment of inertia is what it is, dix plus diy plus diz. Is this clear? And you can write 3di to find the total moment of inertia for a small particle of dm. Is this clear everyone? Is this clear now beta? From this equation or from this symmetry, from the symmetry we have this dix equals to diy equals to diz, and from these three equations what I can write, 3 di equals to dix plus diy plus diz, and it is going to be when when we are going to add these three equations, when we are going to add this equation number 1, okay, when we are going to add this equation number 1, 2 and 3, so this dix, diy, diz is nothing but it is going to give me 3 di 2 dm. Okay, just wait, not in this way. Dm we can take common, 2 x square plus y square plus z square. Is this clear everyone? X square plus y square plus z square. Clear na this one? As you can see, we have 2y, we have 2z, and we have 2x also. So the moment I can add equation 1, 2 and 3, I can take common integration dm and I can do this. Now one more basic thing, if I say it is r is a vector, and obviously r is a vector thing, so how you can write vector? R vector basically is nothing but xi plus yj plus zk, isn't it? Clear? And I want to find the magnitude of this. So beta, magnitude of this vector is nothing but under root of x square plus y square plus z square. So if I square this thing, okay, if I square this new equation A, both the sides, so I can do, what I can get? I can get this, isn't it? The right hand side, this 2x square plus y square plus z square is nothing but 2r square, isn't it? The magnitude wise. Clearly, na? It is understand. It is going into your head or not? A little bit complex, a little bit difficult, I know. But try to understand. Okay, just from the beginning, once again, what I am saying, moment of inertia for a hollow sphere. Hollow sphere, obviously, if it is a sphere, so it is a 3D thing. So what I can do, initially, I just pick this small particle, small dm particle, and I find a point which is from the center is x, y, z. A point P is at the side from the center, it is having a r vector x, y, z. So r vector I can write xi, yj, zk, and this r magnitude is x square, y square, z square. Clear, everyone? Is this clear in your head? Okay. Instead of finding total, you can say directly I can do, because it is a vector thing, so I can go x, y, z system. Dix I know x square dm, diy I know y square dm, diz I know z square dm. From this diagram, I can tell you how x square, when it is going to be rotate along the y or z, it is going to relate y square, z square. In the same sense, if I want to rotate this particle, suppose another particle for, any other particle is going to rotate around y axis. So any particular particle which is going to around, or you can say rotate in this way along as z or x axis. So for that, y square is going to be become x square, z square, or any other particle which is going to rotate on y or x axis in this. For that, z is going to be, or you can say z square is going to be y square, x square. And from the symmetry, because we have one pathway, we have one hollow sphere, so I can, you can say, directly equate this dix, dyy, diz. Clear? It is not 3, it is that. Just a minute. Okay. So from symmetry, because it is one thing, it is only one hollow sphere, so I can do this thing. So then the total small integrate, then the total small moment of inertia is going to be 3di, that is dix, diy, diz. When I add all the three equations 1, 2, 3 for dix, for diy, for diz, I get this. And I know this 2x square, y square, z square is 2r square. Now you can easily say that, and you can easily find that if I want the total moment of inertia, which is I, so that is going to be 3 into di integration, obviously from 0 to r, and you can say from point 0, 0, 0 to x, y, z, which is a particular point P. So everything we have in, you can say, without integration, but this small mass can be converted into, or you can say 2r square, and this small mass can be converted into the full mass. So 3 of I is nothing but 2 mr square, and then moment of inertia I is going to be 2 by 3 mr square. So this is how we can find this derivation. Is this clear? That is 2D thing, as you can see. Okay, I mean 3D thing, but we pick a hollow sphere. Clear? So if I want to do this thing, I can do the same analogy, but it is a solid sphere. So instead of this, I need to go into the volume mass density case. I want to find volume mass density. Then dm is going to be 4 pi r square. You can say like this method I tell you now in the beginning. Where it is, just this one. So basically, the main you can say idea behind to tell you this concept. This is important concept. This one, dm rho dv rho pi r square dr. So for 3D thing, if you can put this dv, which is rho 4 pi r square dr, which is dm basically, and di is going to be, I mean for hollow, for solid thing, okay, you can see this, okay. Yeah. For solid sphere, this dm is going to be, I just write it down, di. For solid sphere, di is going to be nothing but r square dm. There dm is going to be r square into rho 4 pi r square dr. Clear? So this r becomes r to the power 5. Okay. This di rho 4 pi, and that is going to be r to the power 4 dr, and obviously 0 to capital R. So when we do this integration, when we put this rho is nothing but mass per unit volume, volume of this sphere is 4 by 3, okay, 4 pi r to the power 3, and that is 3 going to be up. Okay, so when you put this is the total thing. So automatically you can get I just give you a small hint, 2 by 5 m r square. Okay, r to the power 5 comes from here. So obviously the denominator, in denominator we have going to be find 1 by 5 also. Clear na? I see your faces and it looks like, sir, what you tell me, nothing is clear. It is a little bit complicated. I know, I can feel you guys, so don't worry about it. Okay, but obviously you can understand this all the things by yourself. Only and only one way you need to do all the things, what the manner I can do here. Take a pen and paper, watch this lecture very slow speed or normal speed, because I know at normal speed rewatching the lecture is going to be a bit boring. But for this particular small derivation part, you can rewatch this thing again. And why should I say rewatch and do this thing again? Until unless you are not doing by yourself. So believe me, you are going to forget the formulas even, and you don't get the feel like, yes, this is the same proof and this is the case, and that the formulas are written are quite, you can say, acceptable and quite, you can say, true. Clear, everyone? I can just teach, I mean, I can just taught you this all together, this case, A case or B case, and I can say like everything is going to be proved and prove that and ask me out. But I given you this for C case also, because I know the moment I go into the next cases, the complexity is going to be a little bit hard. Clear na? And you can see right now by yourself. So this is the case you need to do by yourself, like A, B, C, at least whatever the cases I tell you here. And then if you want to do, so the next cases you can approach also. Is this clear, everyone? Okay. So the next thing is moment of inertia. I'm not going to define, I'm not going to derive it, don't worry about it. Moment of inertia for homogeneous rigid objects with different geometries, for you can say hoop or thin cylindrical, for cylindrical thing, because it is simply on a cylinder basis, a particle is going to rotate on a circle of radius r. So I center of mass is mr square if it is passing through the axis, and if it is passing through, you can say for hollow cylinder, or for you can say cylindrical shell, it is going to be r1 square, r2 square, easy one, 1 by 2. And you can say solid cylinder disk is going to be 1 by 2 r mr square. You can do that, you can check it out. Rectangular plates, for rectangular plates, simply if I can pick this particular axis, so this is my become again, you can say as a hollow cylinder of radius a, and this is my radius b. So again, I center of mass for rectangular plate also 1 by 2 m a square plus b square, r1 square, this is the r1 square. Okay, just a minute. But I can write I center of mass. I need to remove remove this then also. 1 by 2 m. I can't write that much small. So here I center of mass is nothing but 1 by 2 m r1 to the power 2 plus r2 r2 r to the power 2. Okay, so in this way these are the two things for hollow cylinder, for hoop or thin cylindrical shell, and for solid cylinder or disc, and for this is even for disc. Disc is what? Disc is something look like this. This is your disc of radius r. Okay, means if it is a radius what I'm saying, sorry, if a disc of radius r is going to rotate from this axis which is passing through the center of mass, okay, so then I center of mass for this radius disc also is going to be 1 by 2 mr square. Here everyone, because this can be taken as a solid cylinder. Okay, so these are sorry, these are the important cases. If you want any another cases also, so you can let me know. I think I teach you this here. Then we have two important theorem. I don't know why the NCERT syllabus deleted that portion, but I find it that is important, so I can put it. Theorem of parallel axis, theorem of perpendicular axis, and I'm not going to go into the more depth. Just a theorem, what it says, what it states that, and how you can find it. Clear? Okay. So this is moment of inertia, or you can say parallel axis theorem. So that is very simple. Parallel axis theorem states that if you know the moment of inertia for any particular axis, and if you draw a axis which is parallel to the given axis, so you can directly find the moment of inertia from another axis using this theorem, using this formula which is ICM plus MD square. And very basic thing, very easily we can do this. Suppose this is your hollow sphere, or you can say ring, right? So for this particular thing, we know this thing. This is the, if the axis is passing through from the center of mass, so that is ICM, axis I, or it is passing through center of mass thing. So ICM, right now we can find 2 by 3 mr square. Is this clear everyone? Clear na this thing? I mean, if a particle is rotating in this way, so that is, this whole thing, if this particular hole, if this whole hollow cylinder, if this whole hole or hollow, two words I am confusing right now. If this hollow sphere is rotating in this way through the center of mass axis, so this is the moment of inertia, that is 2 by 3 mr square. But if I change the axis, okay, I can put this. Now it's my choice. I want to rotate this whole thing with this I prime, right? Clear na? This hollow sphere is now rotating with this I prime. So directly I prime you can find I plus m r square. Why m r square? Because the parallel axis. Obviously it not look like parallel, but assume this is a parallel. So this parallel axis is r distance away from that, isn't it? This is r distance away from that. So I just put the same formula again. I don't do anything. So you know, when we know maximum cases, we know the moment of inertia from center of mass axis. So we can do this. So beta, this is going to be I prime is going to be 2 by 3 plus 2 by 3 mr square by 3 mr square plus mr square, right? So that is going to be same as a solid sphere. I prime is going to be 2 by 5 mr square. You can do the mathematics. It's very easy. if you can take mr square common, so 2 by 3 plus 1, and the LCM of 2 by 3 plus 1 is 5. It is going to be 5 by 3 or 2 by 5. Wait, I am confused in this. 2 by 3 plus 1, that is going to be 5 by 3. 2 plus 3, it is going to be 5. Okay, yeah, it is going to be 5 by 3. Is this clear, everyone? So you can see directly for a center of mass thing, for a hollow sphere, when a hollow sphere is rotating around a center of mass, so that is the 2 by 3 mr square. 2 by 3 or 2 by 5? 2 by 3 na, yeah. So that is 2 by 3 mr square for hollow thing. And the moment I can change the axis, it becomes 5 by 3 mr square, and that is how we can find it. See, this is the point of a center of mass, okay, and I want to find the moment of inertia from this z axis, another axis. Now I change my axis. The moment I change my axis, this is the perpendicular distance. The perpendicular distance is d, and the whole mass is going to be remain m. So this is the parallel axis theorem. Is this clear, everyone? In a same sense, we have a perpendicular axis theorem also. Okay, that is the same analogy. Same thing written over here. I is about any axis parallel to the axis through the center of mass of object. ICM is axis about the center of mass, and D is the distance from the center of mass axis to the arbitrary axis. This is your D axis. This is your distance D. Another axis I prime you can write, and that is ICM, axis of center of mass. Next thing is perpendicular axis theorem. So in a same sense, in a same way, if we know the moment of inertia around this axis Iy, around this axis Ix, so we can find the moment of inertia through Iz. So Iz is Ix plus Iy, and for any planar object, since this theorem states that Iz equals to Ix plus Iy, and since the x and y axis are identical symmetry, and same sense because R, if again the same analogy I can put along this R, along this Z, this Z is square is nothing going to be x square y, right? Clear na? So if I want to find Iz, so beta Iz is simply what? Iz is what? Simply Iz is nothing but mz square, isn't it? Instead of R we can put Z. So in the same sense, Iz is going to be m z square, just multiplying here m. So we can multiply here as well, and that is nothing but Ix, and that is nothing but Iy. So we don't need to give the proof, it is already proven there. So Ix plus Iy is going to be 1 by 4 mr square for any particular disk. So that is why whenever it is passing through the center of mass, or you can say Iz, it becomes 1 by 2 mr square. Clear, everyone? Again, I am saying the proof and this statement of theorem is, you can say, deleted from your NCERT chapters, but it is important because when we have, you can say, shapes of odd shapes. Basically, odd shapes means combination of shapes. Like we have a half circle, then plate, and then another half circle. Or if we have a 3 circles putting together, and the axis is going to be changed. What I'm saying, just a look about it, what I'm saying right now. Then in this case, you are going to find these theorems very, very helpful. Okay, so suppose these are 3 circles, or you can say disc. These are rotating around their center of mass initially, but what I'm saying right now, I want to find the I want to find this particular moment of inertia only about this axis for this body. Okay, is this clear na? So now, if you know the moment of inertia for this particular thing, which is I prime 1, and for this particular thing, which is I prime 2. Okay. Suppose this is your I2 axis, this is your I1 axis, and we want to find from the I3 axis. Clear? So there are two ways. Either you can use parallel axis theorem because it is parallel, but it is not parallel, so you can use perpendicular axis theorem. Ix, Iy, Iz. Obviously, exactly not look like this, and maybe it is going to be the whole body is going to be rotate along this axis also. This middle axis. This middle axis. So in all together, then we are going to use this two theorem. Whatever the theorem is going to help us out. Clear? Okay. If it is clear, so then you do this question then. Okay, quickly you can do this question. Three identical thin rods, each of mass m and length l, are joined to form a equilateral triangle frame. The moment of inertia of the frame about an x-axis. The same thing what we discussed a moment ago, I given to you. So you can tell me the moment of inertia for this kind of thing. Do that. Or should I discuss this thing? Because I think you can take time. Okay, the two of questions I can discuss and then you can focus on this. First of all, tell me, is this clear to you what it is states? Three identical thin rods, each of mass m and length r, joined to form an equilateral triangle. So how you can form? Suppose this is length L, this is length L, okay, and this is length L. Clear na? And all the three have mass m, m, l, l, l. So it can become a equilateral triangle. All have mass m. This is also m, this is also m. First of all, this is given. The moment of inertia of the frame about an axis parallel to the one side. So I can choose this axis. This is the axis parallel to this side. Clear na? If you want to, you can choose this axis also, beta. It's your choice. This axis is, okay, not this one. This one, yeah. This axis is parallel to this side. If another student wants to say that I am not happy with this, okay, you can be happy also. You can choose this axis. It's your choice what particular axis you want. But the axis needs to be parallel one line, one side. Okay, so I found I1 easy. Along the I1 I can teach you. I can teach you another way also, but I2, I3 is going to be a little bit difficult to understand what is going on. Clear na? So I can choose I1. But the question states that this frame, this equilateral triangle is rotating around this axis. Somewhere look like this. It is rotating in this way, around this axis. This whole frame. This equilateral triangle is start rotating around this I1. So taking I1 as a main diagram, we are going to stick to this. So then it is very easy. This is L, and this is L also. And we know that moment of inertia of each rod, AC and BC, about given axis OO prime. IAC, IBC is going to be sine square 60 degree, because as you can see, if this is going to be two components, so the two components is going to be sine and cos. And around OO prime axis, I want to find the sine component of this rod system. So ml square by 3, because I want to find this moment of inertia from you can say one end. So one end mi of a rod from one end is going to be 1 by 3 ml square. And for this you can say AC, and if it is point C, for AC and BC it is going to be sine 60 degree component, means sine component we are going to find, and that is going to be sine square. So L is basically here L perpendicular, because what it is in general, L is going to be perpendicular. So L perpendicular here is L sine theta. Clear? Is this clear now, everyone? For this AC and for this BC, The L prime, what we can put here is L sine 60 degree, and that is why IAC, IBC is ml square by 3 sine square 60 degree, and that can convert it into the ml square by 4. And moment of inertia about road AB. AB is perpendicular to this axis, so that is going to be this median thing, or you can say this perpendicular. So it is root 3, or you can say root 3 L by 2. This D, because I don't want to find the moment of inertia around this axis. This is the road axis, but I want to find on this axis. So I know from this that is the center of mass, but I want to find I prime, that is ICM plus MD square. MD square, and that is the D. Where D is this, you can say perpendicular, you can find L by 2 L, and that is root 3 L by 2. So that is IAB M root 3 L by 2. This one root 3 L by 2 to the power 2, and that is going to give us 3 by 4 ml square. Okay, so when we add all the three, IAC, IBC, IAB, ml square by 4, ml square by 4, 3 by ml square by 4, so we can get 5 by 4 ml square. The correct answer is B. If you have any question query for this, you can ask me right now, because that is going to be a little bit troublesome if you don't understand here. Tell me. Is this clear? Okay, on the diagram, okay, understand this again. We have a 3 roads. Suppose 1 road, 2 road and 3. So the 3 roads going to make a equilateral triangle of length L. Okay, fine enough. Mass M. We can pick any particular axis, but that particular axis is going to be parallel to any side. So I can choose this I prime axis. And these are the points A, B, C, and this axis is nothing but OO prime, and that is the same thing we draw here. Clear? As we know, I is mr square. So beta r is perpendicular. Suppose I pick this axis na. So for this, if this, okay, what is r here? R here is perpendicular distance if it is rotating in this way, isn't it? So for road also, if I choose this axis, so for this axis, you can say L prime is going to be L sine 60 degree. So for I AC or I BC, this is the formula I can apply. But for IAB, I am going to apply the parallel axis theorem. So IAB is nothing but it is I center of mass, or you can say plus MD square, where D is nothing but under root 3 L by 2. You can find it by yourself also. So we can do this IAB. Okay. I mean this perpendicular distance from this axis is root 3 by 2. So you cannot do this. Wait. MD square. Okay. Because this is the perpendicular distance for this road for AB from this axis. So you can IAB is MD square, where D is root 3 L by 2, and you can do this and put all together. Is this clear, everyone? Okay. The next question is almost in this way. So how you can find this? Okay, first of all, what the question wants to say, read it. We want to find the ratio, or you can say if the hypotenuse of the set square, set to horizontal, the ratio of weights W1 and W2. So we want to find the ratio of W1 and W2, and the same kind of thing is given here. So W1 into AD, W2 into this, and then we have a L cos 60 degree and so and so. So okay, this is from the center of gravity thing, or you can say equilibrium of rigid body thing. So a triangular set square of angles 30 degree, 60 degree, 90 degree, and of negligible mass is suspended freely from the right angle corner, and weights are hung at the two corners. This is the weight R, hung at the two corners of this thing. If the hypotenuse of the set square sets horizontally means if it is you can say going to be at this particular point D attached in this way. So what is the ratio of weights W1 and W2? So the ratio of weights W1 and W2 is going to be 1 by 3 because AB, as you can see this, AB is going to be L. Obviously we choose this particular length L, and AD, this AD is going to be A cos 30 degrees, okay, which is L cos 30 degrees. And then BD is going to be BC, this L cos 60 degrees. So L going to be cancelled here. Cos 30 and cos 60 degrees is going to be play the role. So this MM is going to be cancelled. L cos 60 degree is going to be L root 3 by 2 30 degrees. Yeah. And then cos 60 degrees is going to be L by 2. AC and BD. So then it is going to be root 3 by 2. The answer is not correct in the given format. Okay. So then the main thing is here W1 upon W2, which is BD upon AD. AD here is L root 3 by 2. What I'm saying. BD is L by 2, and that is going to be 2 upon L root 3. If I do the reverse, so then it is going to be L cancel, this cancel. So the correct answer is not B, it is D, 1 by root 3. Okay. Yes. Yeah, right. Clear, everyone? Mass into this weight is going to be the equilibrium thing, and that is like from this particular like where we find the center of gravity thing, weight into center of point, which is length. Okay, mg into x. So x here for this particular case W1 we have L cos 30 degree. X for this particular case W2 we have L cos 60 degree. And when we are doing this thing, so the mass mg is going to be cancelled out, and basically we want to find this ratio of W1 W2. So basically mm is going to be cancelled out, and this length ratio we need to find. So that is 1 by root 3. Clear, everyone? Is this clear, beta, everyone? No, yes, right, no. Okay, almost we done, but still you can open your, we done this particular class, equilibrium of rigid body, principle of moment, center of gravity, and explanation about moment of inertia. As usual, we have this center of mass again in my mind, center of mass. So this is your class assessment test link. Open, everyone, and go through all the 6 questions. Over there. And if you find a difficulty in doing any one of them, so you can let me know. And there is a homework also. Okay. Quickly open this and tell me, is it visible to each and everyone or not? Do that. Is this clear, beta? Open this tab. Visible, everyone? Okay. So try this. Read all the questions first of all. And meanwhile, I can find your this also. Where is your batch? And if you find any particular question which is not understood to you, and you find that is not given, we teach in this class, so you can let me know. I can discuss, I can share how you can do that. Or what you can do, just a minute. What you can do, try all the 6 questions. But I think we done in this. Yeah. Okay, do one thing, try this particular test. I go through the questions, try this particular test, and if you find any particular question, it is not, so you can ask me in the chapter assessment, the next class if I am not wrong, next to next. Okay. And if you find any particular question right now, like it is not understood in your by you, or it is like you don't understand what it is states at least, so you can ask me out. And the students who want to go, or you can say who want to leave, because I know already we crossed the 2 hours, so this is you can do this test by yourself, and you can try any particular question of CA in chapter assessment. We discuss in chapter assessment. Okay, one more thing, there is a homework is important too for this particular class also, and for each particular class. Do that also. Okay, because I can see you guys, you don't want to do, and you don't want to ask, even if I say or ask you to do. After seeing your faces, it's too much. We cannot do right now. It's okay, you can do at your, everyone test is visible now. So if the test is visible, we can discuss in chapter assessment, try CA. Link is there, and I think it is visible for each and everyone. Homework is important too, so do that also. Okay.